Taj.
Alright, so the problem that we'll be addressing is operator inattention is one of the leading causes of boating accidents according to the United States Coast Guard, as well as boat performance is hindered by improper positioning of the rotor. And so the current solution for this is using the manual jack plate, which is shown in this, right here in this video, but it has a limited response time and it hurts overall performance and reduces boat safety. And so our design objective for this project is to be able to design a controller that will automatically adjust the jack plate to the optimal height in order to increase performance and improve overall boating safety.
Some of the things that our device has to be able to do is it has to have hands-free operation. It has to network with current boating technology. It has to have hazard detection features and improve overall boat performance. It has to be adaptable to multiple jack plates, allow for user-defined presets and manual override, and it has to provide alerts to the operator in case of some problems coming up with the software. This is our objective tree. We broke down our requirements into 4 main categories. It has to be universal, which means it basically has to work on multiple systems. It has to have high performance, and since our goal is to improve safety, safety is a big concern, and it has to be really easy to use. In terms of engineering requirements, it has to operate off 12-volt DC power. It has to measure the depth at a rate of 100 hertz, maintain a safe and water pressure of at least 10 psi, although that is going to vary based on the user. Calculate the jack plate height accuracy to within 5%, detect floating objects up to 100 meters away, and it has to provide speed updates every second. It's summarized in our house quality, which you can see right here. At the bottom, you can see our engineering targets.
Alright, so we broke down our system into separate subsystems, which are depth detection, speed detection, floating hazard detection, water pressure detection, height detection, manual and preset inputs, as well as alerts to alert the user. So the first subsystem we broke it down to is depth detection, which we broke down into the following 5 criteria, which requires real-time measurements, having accuracy at higher speeds, having a high enough resolution, as well as being cost efficient and having low power consumption. So the first option we were looking at is LiDAR, which is light detection and ranging. So it's able to provide high spatial resolution images, as well as working faster than sonar by using the speed of light to put the smooth sound. But cons with this system is that it's inaccurate in low visibility conditions in water, as well as it's expensive for this type of application. So the second option we're looking at for depth detection is multi-beam active sonar. They can provide accurate readings while the boat is in motion, and it also has good covered resolution and range. It's able to scan over a large area, and it's very cost effective for what we're working with. The cons that come with it is it can't get readings for upcoming shallow water that's being approached by the boat, as well as requiring compensation for noise that gets added to this. So the third option we looked at was forward-looking sonar, which they would provide depth readings for the area that's in front of the boat that the boat is approaching, and if they provide a 2D or a 3D visual map as shown in the image right here. But cons with this is it is inaccurate at higher speeds. It has a high power consumption overall based on the quality of the image that it has to produce, and it has slower refresh rates because of that, and also overall the cost ineffective. And so whenever we broke down the decision matrix, clearly just based on cost and a lot of the strengths that the multi-beam active sonar has are a lot more significant than all the other methods. So we chose to go with multi-beam active sonar as our depth detection.
In order to improve boat performance, it's important that we know the boat's speed. So for speed detection criteria, we have accuracy, low cost, durable, universal, low complexity, and it also has to have low power consumption. The first option that we found was to use GPS to track speed via location. Pros of this is very durable, it's accurate, and it's also reliable. The cons is that it has a complex data structure, and it also has high power consumption. Our second option was the water speed wheel. This speed wheel had very easy implementation, moderate cost, and it was very universal. The cons of it is it was subject to a lot of interference from cavitation of the water, and it also was limited to speeds that were under 60 miles per hour. Our third option was to use a pitot pressure tube. This system was very accurate, it was low cost, and was also universal. The cons of it, however, is it was not very durable. It sometimes has that same interference as a speed wheel, and it lacked durability. Our last and final option was the electromagnetic sensor. This is a very durable design. It had low maintenance, and it was also accurate. The cons of it is that it requires you to drill a hole through your boat in order to install it. It had limited technology available on it, and was also high cost and high power consumption. In order to decide which one of these options was the best, we used a decision matrix. As you can see, the GPS antenna was twice as high as anything else as far as scoring, so we decided to use that as our primary method of getting speed. And as a secondary, in case GPS antenna implementation fails because of its complexity, we're going to use the speed wheel as an easy fix in that area.
All right, for our floating hazard detection system, we use the following criteria. It must have long-range capabilities. It must have subsurface detection. It must be cost-effective, low power consumption, and it must be easy to install without modification of the boat. First option we looked at was forward-looking sonar. Works the same as traditional sonar, except it uses a forward-facing transducer. It's relatively new, so forward-facing sonar units are very expensive. The problem with the forward-facing sonar, though, is that the surface objects become distorted due to external noise. The next option we looked at was radar. Radar uses electromagnetic waves to detect objects at a distance. Very effective for detecting large objects on the surface, such as boats, land masses, or like large buoys. The problem with the radar is it doesn't attenuate well in the water. The waves attenuate quickly. So, and then objects barely breaking the surface aren't big enough for the radar to detect. The third system we looked at is infrared imaging. A small infrared camera is able to detect objects floating on the surface. Image recognition software can detect a floating hazard based on its heat signature. This works by averaging the intensity of thermal radiation in each pixel. A team called UBC Sailbot Team, they made an automated sailboat, and this is the system they use to detect floating hazards in the ocean. For our decision matrix, we went ahead with the infrared imaging because it has the lowest power consumption, it's the cheapest, and is the most effective at detecting floating objects.
Okay, we need to be able to detect the water pressure and make sure our engine's going to stay okay. So the main 5 criteria are: it has to be cost effective, it has to be accurate, it has to have a low power consumption, it has to be physically small, and we don't want to bother too much with any mechanical designs. So the first option is we can modify an analog sensor. This is great because we can choose all the electrical components, so we basically get to choose the specs of our device with some good reason. Also has a low power consumption. The biggest drawback, though, is we're basically building a new device, so it has a very, very long manufacturing time. The second option is a strain gauge. It is really, really nice because it has a highly predictable behavior, because the strain gauge basically is a resistive material that changes the resistance when it flexes. And also, due to the accompanying circuitry being just a simple Wheatstone bridge, it can have a very low power consumption. The biggest drawback to this is it's very sensitive to temperature changes due to thermal expansion. The third option is a piezoelectric device. This is really great because it doesn't require an external voltage source, because it functions by dumping charge into the system. It's also very, very accurate. However, it's not suitable for static measurements because it functions by dumping charge into systems, which the charge then decays exponentially. So we would need some kind of extra buffering circuit, which can be very complicated. Option 4 is a Dahl tube. It's basically a modified Venturi tube, and therefore it shares all the benefits of the Venturi tube, such as it's accurate, it's reliable, it lasts a really long time, it's durable. The only problems with it is it's physically large, but the biggest problem is that it requires it's very invasive in its installation. You have to actually cut into the cooling system to install it there. So with these in mind, really only one option is truly viable, because the modded sensor has a very long manufacturing time. Piezoelectric isn't really good for static pressure measurements, and the Dahl tube requires significant modification of the engine. So we're going to go with the strain gauge.
Next we have the height detection. The criteria for this was the accuracy, and it has to be universal, and it has to be durable. The first option was ultrasonic sensor. It's accurate, and it's low power, and it's low cost, but the cons of it is it's highly subject to interference. Option 2 was a smart stick sensor. It was like a magnetic sensor with a magnetic pointer too. It's easy to install, it's durable, it's precise, and it's universal, but the con of it is its high cost. And the third option was an analog gauge. It's durable and universal, but we have to convert it to digital, which brings the cost up a lot more, and it's highly inaccurate too. So based on our decision matrix, we decided to go with the smart stick sensor because it is accurate and it's more durable and it's universal.
For user input control, our system will deploy a 3-button operation for the user. These buttons are going to enable him to override the automatic mode and control the jack plate in manual mode. And it's also going to be a way to input presets that he wants to set before he sets out on his boat. For user display, it's going to be very simple, a 7-segment display, something that's easy to read in bright sunlight, and also less distracting for when the boater is driving. It's going to have a preset menu, and it's also going to display the height of the jack plate at the current time.
Now, the primary way that our system is going to tell the user when there's a problem is via an alarm system. It's going to be essentially an audio amplifier connected to an 8-ohm speaker. The main concern about this is it has to have a very low power because like most things on the boat, this is going to be operating off a 12-volt DC power supply, so it has to have a very, very low power consumption. Also, it has to be loud because the average sound intensity whenever you're on the open water at about 45 miles an hour is about 75 to 80 dB. So this has to be, you have to be able to hear this. So simply because of its efficiency, we chose a Class D amplifier because it is the highest efficiency of all the amplifiers we looked at. And if this proves to be insufficient for some reason, then we're going to fall back on a Class AB amplifier.
Next, we selected the criteria for our microcontroller. It required that we had a variety of input-output pins because of so many devices we were inputting. We had to make sure that we had like some analog to digital converters. Next, we needed it to have a fast processor speed, be low power consumption, as he said, due to the 12-volt battery. And lastly was ease of use, because our system, this is the main component of it, and a lot of our EEs, along with our computer engineers, will probably be having to do some sort of coding. So we wanted to be able to work, everyone can kind of put their hands in on it, not just us two computer engineers. So our first option was the Arduino Zero. This system was very simple implementation, low power consumption, and it also had one analog to digital output pin. Cons of it is it had a very low RAM memory. The second option was the Arduino Do. This option had 54 input-output pins, and it also had 2 analog to digital output pins. It had the same implementation process as the Zero we've seen before, and it had moderate power consumption. A con of the system was that it had 92 kilobytes of RAM. Our third option was the BeagleBone Black. This system has the most input-output pins of all the devices we looked up, but it had no analog to digital output pins. It also had a very high processor speed. Our fourth option was the Raspberry Pi. It had 40 input-output pins, it had super high speed, and 1 gigabyte of RAM. The cons of this system is that it was difficult to implement based on our understanding as a group. It had limited analog to digital pins. I think it was 4 actually, but they weren't on the board itself. It was on the expandable board that you had to integrate into your system separately, and it had high power consumption. The fifth option was the Cytron ARM Cortex M0. This board was actually designed after the 2 Arduinos that we looked at before, but the main difference is that it runs on logic of 5 volts rather than 3.3 volts. And it also has 16 pulse width modulator input-output pins. The cons of it was its high power consumption, and it had no analog to digital output pins, and it also had moderate speed.
So based on our decision matrix, the Arduino Zero and Arduino Do were the highest 2, but we went with the Arduino Do because of the input-output pin, and our secondary selection is Arduino Zero because of the low power.
So if we don't need all those pins that the Do offers, then we will drop down to the Zero to save power.
Okay, our control system must be adaptable to the onboard 12-volt system. Depending on the power demand of our controller, we may use an external solar charging system to charge the battery while the engine is not running. Due to the tight budget, we would like to keep the power consumption as low as possible so we don't have to implement this. And we're also going to include 2 5-volt USB output power sources to charge any other accessories on board.
And as you can see, our system integrates multiple different devices that some may already be on boats. So we had a lot of our research say that, hey, we want to be able to integrate systems that we currently have into your system. And the way that this is done today is using the NEMA 2000 networking cable. So we wanted to try and integrate that into our system. And as we were doing our research, we realized that the protocol for integrating this system was $4,500. So we decided that that would be a system constraint that could someday be overcome if we were able to get funding.
And this is our high-level system diagram that displays our inputs and outputs for our device. It displays our inputs and outputs for our device. So, are there any questions?
You mentioned the GPS as a complex data structure. What made it?
Most GPSs run on NEMA 18, I think it's 59. So, and it gives you more than just your location. It gives you time, it gives you how many satellites you're connected to. Basically, you have to extract the data you need. So that's what I meant by complex. Any other questions?
First, Cody, did you see, all I'm looking for is that last slide there. I'm okay with your decision arguing because you presented 3 alternatives that were not arguing with, and explain why that's okay to go with arguing. I wanted to point that out, so that's really the only thing. So you can go with the argument of those other job. So why did you have to put it at 100 hertz? Why is that a spec?
Because, well, at that, operating at that frequency, we want to be able to, so at the average boat speed is around like 45 miles per hour, and that's like getting about around like 20 meters a second. And so we just wanted to be able to take enough measurements every single second, so at that speed we'd be able to get at least like 4 measurements a second, which would be multiple measurements every single meter. So we wanted that kind of accuracy.
Okay. How is speed measured typically on a boat now?
It is measured 2 ways. One is GPS, and the second measurement is kind of like the pressure pitot tube, but that tube is mounted inside of your motor. Either people use the pitot tube, and most boats you see driving around the interstate, next time you see a boat, look for the pitot tube hanging, and it's literally going to be hanging because it's probably broken. But the ones that are inside of the motor, what happens in Louisiana a lot is you hit a lot of logs, even small logs, and it clogs that hole, and your speed just doesn't work. So most boaters rely on GPS.
Okay. I got really excited when I saw that IRA. Yeah, that's going to be fun. I'm glad you guys going with that. And, you know being a physics major, you probably know a lot more about this kind of thing than we do, but I had no idea what a Venturi tube is. We talked about it like it's a straw. So just keep that in mind, that sometimes, your audience isn't up to speed on some of the things outside of our world. So I'm curious, I'm gonna look up what a Venturi tube is now, but I didn't know what it was. Kind of felt dumb for something to talk about. Yeah, so what is it?
It's basically a section of pipe that is constricted, and then you have another pipe that goes underneath it with a fluid in it that has a known density, and as the air or water or whatever fluid it is goes above it, it creates a pressure difference due to the speed, how fast the fluid is flowing through the pipe.
Because the speed is
Because it's
lower
faster.
and